Energetic 7b, Entropy and Spontaneity 2, the Spontaneity and Gibbs free energy. Essential idea again is that a reaction is spontaneous if the overall transformation leads to an increase in total entropy, that's system plus surroundings. The direction of spontaneous change always increases the total entropy of the universe at the expense of the energy available to do useful work. This is known as the second law of thermodynamics. Nature science, theories can be superseded. The idea of entropy has evolved through the years as a result of developments in statistics and probability. What have we learned so far? Well, we know that spontaneous reactions occur without the continual input of energy, and they may be slow, fast, or somewhere in between. Reactions tend to proceed to a state of lower energy. And so exothermic reactions with negative enthalpy changes tend to be spontaneous, and endothermic reactions with positive enthalpy changes tend to be non-spontaneous. Spontaneity and entropy. Reactions tend to proceed to a state of higher entropy, greater disorder. Reactions with increasing entropy tend to be spontaneous. So reactions with decreasing entropy tend to be non-spontaneous. Oh, and there should be a little triangle in there, shouldn't there? Indicate the signs for the change in enthalpy and change in entropy associated with spontaneous and non-spontaneous reactions. Can you do that? Let's pause and have a go. Okay. Well, spontaneous reactions, the enthalpy is negative and the entropy is positive. There's an increase in disorder. For non-spontaneous reactions, the enthalpy increases, but the entropy decreases. Have a think about this elastic band reaction here. You've got a contracted elastic band, which is kind of all wiggly, and you've got a stretched elastic band, which is tight. What is the sign of delta H for the forward reaction? The forward reaction is denoted by this top bit here. I don't know if you've seen this before. Okay, forward reaction. What is the sign of delta H for the forward reaction? Well, will it go that way automatically? Or do you have to put energy into the system? You do, of course, need to put energy into the system. So it is going to be, what is it going to be? That's right, it's going to be positive. Okay, it won't happen spontaneously. What is the sign for the reverse reaction? What is the change in entropy for the reverse reaction? That would be going this way. Well, it is going to go spontaneously, so it's going to be positive delta S, isn't it? This is more disordered, and the reason is that the polymers inside the elastic are kind of all lined up and orderly there, and they're disordered in this one. So, which reaction is spontaneous? Obviously the one going this way. You don't need to include energy for it to occur, it's going to happen. Enthalpy, entropy and temperature all play a role in determining the spontaneity of a reaction. And this bloke here, Josiah Willard Gibbs, came up with a very helpful theory. He proposed a solution to the problem by defining a quantity known as free energy. Gibbs free energy. Gibbs free energy is a measure of the balance between... Gibbs free energy is a measure... Oh, what's going on? Let me get to that. Oh, let's try that again. Gibbs free energy is a measure of how the balance between temperature, entropy and enthalpy affects a reaction. Gibbs free energy reflects the ability of a system to do useful work, such as building tissues or efficiently burning a fuel. Gibbs free energy is calculated using the equation. You've got the change in Gibbs energy equals the change in enthalpy minus the temperature multiplied by the change in entropy. So Gibbs free energy, the unit is kilojoules per mole. Standard enthalpy change is the kilojoules per mole. Temperature in Kelvin, and the standard enthalpy change is in kilojoules per Kelvin per mole. A negative change in Gibbs free energy indicates a spontaneous reaction, and a positive change in Gibbs free energy indicates a non-spontaneous reaction. Can you predict the sign of delta G for the following? Well, if we've got a negative enthalpy, we know it tends to be spontaneous. If we've got a non-spontaneous reactions have positive enthalpy changes. A positive entropy, so an increase in entropy, tends to be spontaneous, and a decrease in entropy tends to be non-spontaneous. And so a negative change, you can see here if you just plug them in, a negative delta H and a positive delta S, negative times a positive is going to give a negative. So a negative plus a negative will definitely give a negative delta G, and so that is going to be spontaneous at all temperatures. Here, if we've got a positive delta H and we've got a negative delta S, negative temperature multiplied by negative delta S is going to give us a positive. So we're going to get a positive and a positive, so delta G will be positive, which means it's not spontaneous at any temperatures. If we've got a positive delta H here and we've got a positive delta S, the delta S is multiplying by this negative T. So depending on the size of the temperature, the smaller T, the smaller the delta S, the smaller the negative delta S. Okay, so it's going to be spontaneous at high temperatures. If you've got a large negative T multiplying with delta S, your delta G is going to be negative. And if it's negative, then it's going to be spontaneous. Over here, I'm going to put both in. If you've got a negative delta H, you want this to be not to be too largely positive. Okay, so you want the temperature to be as low as possible for it to be spontaneous. Example 1. Got ozone going oxygen going to ozone here. Delta H is positive. Delta S is negative. It's becoming, you've got 3 moles of gas to 2 moles of gas, so it's going to be negative. And so you've got positive delta H and negative delta S. Negative times a negative is going to give another positive, so you're going to get a positive delta G. Positive at all temperatures. The reaction is not spontaneous at any temperature. Sorry. Predicting the sign of delta G. Example 2. You've got octane, the combustion of octane, and delta H is negative, so the enthalpy change is negative, and the entropy change is positive. We've got 21 over 9, so you've got like 10.5, 11.5 going to 13, so you're getting an increase in entropy definitely. There's an increase in particles of gas as you go along this way, so entropy is increased, disorder is increased. So you've got a negative delta H, you've got positive delta S, so positive multiply a negative is going to be negative regardless. So, oops. The change in Gibbs free energy is negative at all temperatures, so the reaction is spontaneous at any temperature. Example 3, we've got evaporation or boiling. The enthalpy change is negative. The entropy change is negative also, because you're going from more disorder to less disorder. We put those in, a negative delta H and a negative S. That's going to be a negative and a positive, so it will depend on the temperature, won't it? So the change in Gibbs energy is negative only at low temperatures. The reaction is spontaneous only at low temperatures. To calculate the change in Gibbs free energy, we can just use the formula. And you have to find delta H first, then delta S, and then delta G in that order. And then you look at the sign and you can tell if it's spontaneous or not. Delta H is given in this question, and it ordinarily will be, or you can look it up. You get out your data booklet, and you can find out the change in entropy using the formula that we've already looked at. Then again, you just use the formula that we looked at before using your calculator, and then you find out the sign. So let's do that. Delta H was given. Delta S, we use the change in entropy of products of the sum of the change in entropy of products. Oh no, there's a huge whirring sound starting. Hopefully this won't spoil the audio too much. Minus the sum of the entropy of the reactants. So we've got the entropy of the ethane minus the sum of the entropy of ethene plus the sum of the entropy of hydrogen. Plug in the figures and you get the change in entropy. And you want it in kilojoules per mole, so you use this here conversion factor to get your answer. To find the change in Gibbs free energy, we use this formula and we'll just plug in the change in enthalpy that we know, and then plug in the change in entropy, which we know too. Make sure you get the units correct. And we were given the temperature to find change in Gibbs free energy. It is negative, and so it is going to be spontaneous. Method 2. You can look at the sum of the change in free energy of the products minus the sum of the change in free energy of the reactants. And this can show up on exams. To find the change in Gibbs free energy for this reaction, 25 degrees Celsius. You get a little table there with all the information you need. And so you can write out the formula and just plug in the numbers. You've got products minus reactants. The product is C3H6, and you've got the reactants. We've got C3H4 and hydrogen, and so you just literally plug them in, do the math, and you find that it is a negative, so it is going to be spontaneous. There's a file on Moodle that you can have a look at and just have a play around with this thing, but just have a quick look at this. It says at what temperature will the reaction with the change in enthalpy and change in entropy values shown change from being spontaneous to non-spontaneous. You can see we've got temperature along the bottom here, and we've got Gibbs free energy on the y-axis. When Gibbs free energy is negative, below here it's spontaneous, so anywhere below this temperature here is going to be spontaneous. Anything above this temperature is going to be non-spontaneous. So below about 220 Kelvin, the reaction is spontaneous. Above 220 Kelvin, it is non-spontaneous. Example 1. Given this reaction, C2H4 plus hydrogen gives ethane, and we're given both the change in enthalpy and change in entropy. Or what temperature will the reaction change from being spontaneous to non-spontaneous? It might seem a bit tricky, but it's very straightforward. You'd write down the formula that we know, and the temperature, or what temperature will the reaction change from being spontaneous to non-spontaneous, is when the Gibbs free energy is 0. So we'll have the Gibbs free energy too. And so the only unknown in here is temperature. You can plug in the numbers. Make sure you change joules to kilojoules if a question doesn't have it in. Do the maths and you get your answer in Kelvin. Example 2. We know that the change in Gibbs free energy for this reaction is -132, we saw previously. At 25 degrees this reaction is spontaneous. We want to calculate the temperature at which the reaction will become non-spontaneous. So write out the formula. We'll have to find the change in enthalpy first. The change in enthalpy is the sum of the change in enthalpy of the products minus the sum of the change in enthalpy of the reactants. Plug in the figures from a data booklet or from a table if it's given in a question to find the answer. Oh, that seems to be the wrong way around. Then you can find the change in entropy, and again it's the change in entropy of the products minus the change in entropy of the reactants. Plug it in from a data booklet or if they're given in a question. And then you find the temperature at which delta G is 0, like we did before. And so you plug in what you just found, the enthalpy and the entropy, and you can rearrange to find the temperature. And if you can change it to degrees Celsius if required. Splendid. And my apologies about that drilling in the background. There's not much I can do about it.